Hi, good evening, everyone. I'm delighted to welcome you to the fourth event in our series of Welcome to Rail induction events, organised in collaboration with YRP and Network Rail. So this event today is called Staying on Track, an introduction to track and infrastructure, and we've got a great lineup of speakers from Network Rail today to talk about everything track and infrastructure. So these events are designed to be educational, provide early career professionals with knowledge, key understanding of concepts, issues, opportunities, and challenges facing the industry today. Of course, if you're not an early career professional, you're still welcome. We hope you learned something new. The Welcome to Rail initiative will also eventually provide some networking opportunities for those who have attended these events, and YRP and Network Rail are working to bring these to you in early 2022. So we've had 3 great sessions already. We've seen speakers covering the history and the future of UK rail. We've had rail leaders covering challenges and opportunities faced by the industry. And last week, we had some really good speakers talking about rolling stock from kind of design stage to refurbishment and delivery. So before I hand over to Erica from Network Rail to do some other opening remarks, I'll just quickly go over some housekeeping and say a little bit about young rail professionals. So throughout the presentations, you'll see you can submit questions to the speakers, which you can just do in the chat box to your right-hand side. And after everyone's gone through their presentations, we'll then go through a Q&A. Just to quickly tell you about YRP, it's a voluntary organisation and it spans the entire UK. We have volunteers all over the country, and everyone kind of gives their time to put on these events to just help people have like personal and professional development. We work to promote, inspire and develop the next generation of railway talent, and we aim to be kind of inclusive, collaborative. We try to lead by example, and we also try to have lots of fun at the same time. At least we think we're fun. So without further ado, I'm just going to hand over to Erica Diaz from Network Rail, who's just going to talk a bit more about the speakers and Network Rail's role in this. So over to you, Erica.
Thank you, Isabella, and welcome everyone. Very excited to have you here this evening. As Isabella mentioned, we've been working in collaboration with YRP in Network Rail on designing this Welcome to Rail induction program. And we at Network Rail are very excited to have been working in designing this for you. I understand personally how difficult it is to join an industry like us. Lots of acronyms, lots of jargon that if you are new to the industry, you maybe don't understand how everything works together, how the infrastructure signaling and everything that we have in the industry comes and joins together. And obviously, it's important that we provide this platform for new people in the industry, but for those that are not new, for example, myself, I'm not new, but I learn a lot of things. I work in a HR corporate environment, and I'm not too familiar with all these practical and operational things from the industry. So the better you learn, the better equipped you are to evolve your own career and to play a part, obviously, in connecting and collaborating to shape and drive our industry is fantastic. We really hope that you enjoy maximizing the opportunity that we're offering with these programs, and we're really pleased to have joining us lots of experts in track from Network Rail today in this session, and we have a great lineup, as Isabella mentioned. We have Kamini, I'm sorry if I can't pronounce your surname well. Kamini Edgley, who is going to be having an introduction to us. Brian Whitney, Mark, unfortunately, cannot be here today. Brian, Jayden, and Richard, and Gareth, who is going to be sharing the expertise and the knowledge about track with us. And without further ado, I don't know who will be presenting the next slide, Isabella? That is you, Jacob, in the background. Great.
Perfect, thank you, Erica. Right. So yeah, we'd just like to introduce our first speaker, Kamini Edgley. Thank you, Kamini.
Thank you, Isabella. Good evening, everybody. I'm Kamini Edgley. I'm the Director of Safety and Engineering within Northwest and Central Region, and delighted to be speaking with you today. I've worked within the industry and Network Rail for a number of years now, and I have thoroughly enjoyed my journey so far. Next slide, please, Jacob. I'll start by telling you a bit about myself. And really, you know, my focus today will be about the stuff you don't get taught about, that you need to be able to survive, be yourself, and lead within the railway industry. As you can see from the photos, I was born in the idyllic island of Mauritius and grew up there before I came to the University of Leeds to study electrical and electronic engineering. Apart from being a beautiful touristic place, Mauritius has also got a very diverse culture, as all the inhabitants migrated there because there was no indigenous population, obviously apart from the famous dodo that used to reside there. So for me, diversity and inclusion is very much part of my DNA. The bottom two photos are that of my family and also my direct report, who is my extended family, really. Because for me, it's not necessarily about work-life balance, but it is about life balance, as work is very much an integral part of it. And if any of us wants to be successful, then we need to be able to be who we are and bring our whole self to work and be accepted for who we are as well. So we're always psychologically safe and can give the best of us to our work. So next slide, please. So in terms of my journey into engineering, after finishing my degree, I was lucky enough to be able to get on a management graduate signaling training scheme within the railway industry. This allowed me to achieve chartered status with the Engineering Council, and currently I'm a fellow of the Institute of Engineering and Technology and also the Permanent Way Institute. And additionally, I've got a postgraduate in strategic and business leadership from the University of Warwick. And I've got a Six Sigma champion because for me, I always promote continuous improvement, as you will see later on. So piece of advice from me would be, especially at the start of your career, to ensure that you always work towards professional accredited status and get that rounded experience if you want to get into an engineering leadership role. My career path and journey has really helped me and continues to help me. And somehow, for whatever reason, I've never gone for what has been perceived as an easier option. Because when I finished my training, I was again lucky enough to secure a maintenance engineer role in a busy part of West Coast Main Line South. And that basically threw me into the deep end. But what an experience, and to this day, the experience gained in that role still helps me as a director of engineering, so hard work really pays off. After doing my spell in maintenance, I moved into the project world and worked for Bechtel while still being employed in Network Rail on West Coast Route Modernization Program. And that's effectively when I did the switch from engineering into project and program management. After doing that, I decided I wanted to do something completely different and went into business change. And as part of my role, I was responsible to deliver an efficiency of 3.2 billion, which again took me out of my comfort zone totally, because all of a sudden I was managing 18 programs with no direct line reporting. So I had to really hone on to my influencing skills to deliver the right outcomes. Once I did that, I took a year off to have my little girl. And when I came back, I took on another challenging task of managing electrical safety. Richard, who's speaking later on, can tell you all about that. At the time I took it on, the company was being prosecuted by the regulator for failing to deliver improvement in that area. This led to the creation of the Electrical Safety Delivery Program, which to date we've spent for the past two control period over £500 million. Following that, I got promoted into the Chief Mechanical and Electrical Engineer role, where I had a portfolio looking after not only OLE, conductor rail, power distribution and system, but also rolling stock and plant. I also did a year as chief engineer for Network Rail before taking on my current role as director of safety and engineering, which I am thoroughly enjoying. So again, for me, don't be afraid to take on challenging roles, especially in your early career, because the experience you will gain will hold you in good stead for the remainder of your life. Next slide, please. So what do I do as Director of Safety and Engineering? Well, amongst other things, I strive to deliver engineering excellence. And how do I do that? Through technical competence, critical thinking, and continuous improvement. Let me explain. If we can move on to the next slide. One of the most important things in the railway industry is this diagram. You've probably seen it before, and you've probably also heard about engineering excellence. How does engineering excellence culture help to deliver the service equation? And what is the line of sight? Basically, through technical competence, critical thinking, and a continuous improvement mindset, you deliver an engineering excellence culture which subsequently gives you better safety and performance. And together with doing the basic brilliantly, you deliver an outstanding service for our passengers and freight users. It's quite simple, really, but it is very much integrated. So you have to have all three to deliver, and you have to have the right foundation to get the desired outcome. If we can move to the next slide, please, Jacob. How do I, therefore, lead my team to deliver engineering excellence? Just keep going, Jacob. So, firstly, by creating the right individual and organizational culture. We need to make sure we get the right people in the right places based on competence, cognizance, commitment, accountability, and passion. So there is openness, trust, and integrity. Secondly, by developing a team which has the right technical understanding and execution. So they have the right competencies and capability. They have in-depth knowledge and expertise. And the speakers that are going to come after me, my God, they are experts in their field. And I'm sure they'll bowl you over. We need to be able to do technical execution through whole system thinking. So not looking one-dimensionally, looking at the whole system. And in terms, create smart objectives and KPIs which are aligned and have a balanced workload. Thirdly, to complete the triangle, we need to create the right partnership within the company and the wider rail industry. So ultimately, we can always put our passengers like Gail here first. If you look at it, it's very simple. But because it involves people, there is a lot of care and attention that needs to go into it to get the right capability to deliver the right outcome. Can we have the next slide, please? This really comes to life in my transformation program that is known as the 10-point plan that I'm currently delivering. It is a bespoke, holistic approach to tackle the systemic problems that we have. As you can see, it is effectively a tempo. It improves our approach to engineering and asset management. Ultimately, it will deliver engineering excellence in the region, which will enable us to provide a great service to passengers and freight users, and also set us up for success for future control periods. We're all very busy working through CP7 and making sure we get the best settlement possible, and we deliver taxpayers' money in an efficient way, and get a railway which is fit for purpose for the future. And all of that is going to, for us, in my current role as part of delivering excellence, is being done for the 10-point plan. So it's basically a set of delivery groups, as you can see, which has got enabling pillars. And the pillars are things I've spoken about, which is competence, capability, risk management, data, information, technology. And the foundation is based on the culture, and effectively the delivery groups are done for the different business units within the function that I'm looking after. So all these changes, we really have tangible and sustainable outcomes. Already we've seen greater efficiency, a more competent and a more engaged workforce. And this means, together, by delivering all the different components, we take a holistic approach to deliver engineering excellence for the business, which effectively gives us a better railway. If we can move on to the next slide. It's also important to look at the railway as a whole system and to take into account system integration, which we all know is the process of bringing the different components and subsystems into one system so it delivers the overarching functionality, ensuring that the subsystem function together with a system, lots of systems word, is a coordinated whole. So system integration is not just about technical systems, it must also incorporate non-technical interfaces and subsystems. So effectively looking at the system overview, the safety, the cost and performance, and all the different components that sits within that. Could we have the next slide, please, Jacob? There are a wide spectrum of different people with lots of wheels that we need to help keep turning to deliver a safer, reliable, and affordable railway, especially in the current climate where we are very cash constrained. So it is important that we're inclusive and accept each other, so we always create the highest performing team that will deliver the best outcome. I would like to conclude by saying the world is your oyster. The railway industry offers significant opportunities for people who want to learn and make a difference. It is not always easy, and there is always going to be challenges, but be determined and you will succeed. I'd like to leave you with a quote from Kamala Harris. Dream with ambition, lead with conviction, and see yourselves in a way that others may not, simply because they have never seen it before. Thank you, and the very best of luck in your railway career.
Thank you, Kamini, and really like the combination of career advice and engineering knowledge. That was really actually very inspirational. So thank you very much. And yeah, it's great. I know you won't be here for the Q&A, but if anyone has any questions for Kamini, they can just send them in and we'll email them over to her, then she might be able to get back to you personally. So thanks so much, Kamini. And
thanks a lot, Bella.
Thank you.
Enjoy the rest of the session. Bye-bye.
Thank you. So our next speaker is Brian Whitney, and Brian, I think, will also be covering the session from Dr. Mark Burstow, who has unfortunately been called away to the site of the accident in Salisbury today. So over to you, Brian. Thank you very much.
A little bit of background. I'll just attempt to share my screen. Let me just move that across. Can people see that as the screen as a presentation?
Yeah, we can see the presentation.
Let me just try and make that. Does that still visible there?
That's fine. Yeah, you just need to change it to the presentation rather than the presenter mode on the display settings at the top of your screen.
Bear with me a second.
So yeah, the display settings option just in the middle at the top.
I've got it on 2 screens. Apologies for that. Yeah.
Cool. And then just swap presenter and slideshow.
That better?
Perfect.
Excellent. No, thank you. Good evening, everyone, and thank you, Kamini. Thank you for that. Thank you for the opportunity to have a chat and really go through a bit about track infrastructure, is where I've spent a lot of my career. Just as a very bit of background, I started in the railway in 2000. I originally came as a specialist materials engineer, very much looking at broken rails and rail defects. I came originally for 6 months, but 21 and a bit years later, I'm still here. So I found it quite a fascinating place to work, a lot of opportunities. So something that I thought it was perhaps quite a mature industry without much change and challenge, but I found that very different. So fascinating time I spent with that. So hopefully some of that I can go through fairly quickly to explain a bit about what track is, what's involved, why it is not a simple thing, why it's quite complex, why it needs careful management. And apologies from Dr. Mark Burstow, he's our principal vehicle dynamics engineer, so very specialised in what happens between the wheel and the train and the rail and the impact of that. He's also our head of our derailment investigation team, and unfortunately because of the incidents at Salisbury is heavily involved in that at the moment, so wasn't able to be here tonight. A little bit about the UK track network. We've got about 33,000, nearly 34,000 kilometres of track, and it's made up of different types of component. The primary one, it's all welded together as continuously welded rail. We do have some older designs of track which are bolted together with joints. We have a lot of different rail sections from different ages, and starting slowly to change that to a more modern construction. But a number of existing bits still exist around the network. And in addition to the plain line track we've got 19,800 units of S&C. These are switches and crossings, which are used to change the direction of the train from one track to another. A little bit about electrification. I think Richard will show a lot more. Proportion of our network is electrified. We have different types of electrification. Our main lines tend to be electrified with 25,000 volt overhead line, but in the southeast corner, we have a large amount of 650 or 750 DC through a third rail. And in the northwest, we have some areas with 1,500 volt DC overhead line equipment. So a very big mix of infrastructure there. I won't go through too much of the details. Originally, we were structured as 5 regions with 10 routes, but we're now moving to a slightly new structure with 5 main regions and comprising of 14 routes in total, including the high-speed line across to the southeast of England. A little bit about the asset base. It's very large. It's dispersed around the whole country. As I said, we've got 34,000 kilometres of track, and that's about 50 million sleepers and about 42,000 miles of rail. But in addition to that, there's over 40,000 bridges and tunnels, over 2,500 stations, 830 signal boxes, 7,000 level crossings. But we also have 8,200 commercial properties around stations. We're currently around 40,000 employees, and I think still the largest private landowner in the UK, and the largest or second largest consumer or purchaser of electricity in the UK, but also with a large telecoms network to support the operations. We've got a lot of things in common with other utility companies. Our assets are pretty diverse and dispersed around the country. We've had quite low levels of investment historically. Infrastructure is a very large mix of different ages, and we have significant demands for improved serviceability and efficiency and safety, and some big drives for cost efficiency. And historically, it's not something where we built a lot of new railways in the UK. Most of our railways are historic, and a lot of our maintenance and renewals is a spot replacement and fix rather than a building of a new line. There's some big challenges as well. We're a high hazard sector, so we're grouped with the Health and Safety Executive with nuclear installations, offshore oil and gas, chemical manufacture and storage. So quite a challenge there in that we are considered a high risk. We've got a large number of interfaces and system dependencies, so it takes a lot to make the railway work on time. We have a high rate of usage, particularly in track, driven by degradation. So it's continuously wearing out as we're running trains, and the significant interactions, which I'll talk about a bit more later on, that cause damage and wear. We've got a lot of complex relationships and interfaces between industry parties, and we're heavily regulated. So quite a challenging industry, but I think a lot of those challenges make it an interesting industry to work in. It's not just tracks, signals, stations and bridges. We've got 14,000 miles of fencing. We've got about 9,000 miles of bespoke drainage rather than just culverts and gullies, but these are pipe drainage. We've got about 2.5 million trees immediately on our land, but we've got about 5 million in the land adjacent to our infrastructure, which could fall or disrupt our infrastructure. And in 2013, we had over 1,000 incidents of trees on the line and 30 people hurt as a result through the year. So it's something we've got to be mindful of there. It's not just keeping the rails in the right place, but the surrounding vegetation needs management. And some examples where a tree there that's blown over has blocked the line, and the work then to clear that and remove the debris so that the track can be replaced. The trains can continue to operate. A lot of work there, and how we manage that, and the trees, like most things, that's continuously changing, different from different seasons, growing, perhaps disease and other things that affect them as well. A bit about our expenditure. This is looking at a chunk of a chart here. Track at the moment still has slightly, or just about the highest expenditure out of the main disciplines. So about 31% track, signalling about 21%, civils about 18%, and buildings about 7% of the track there. Larger proportion of track is plain line track and replacement. There's a significant spend on S&C, the switches and crossings, and then other. So a bit of an example there. It is a lot of money. I think, as Kamini said, it's quite a challenge when you look at the size of the numbers there. In CP5, which is the control period that ran from 2014 to 2019, we spent nearly 13 billion on replacing assets. We spent a similar amount on expanding the network with enhancements, about just over 5 billion on maintaining it, and then a further 3 and a bit billion on support, which includes things like energy costs, electricity, that side of things. And on average in a year, about 3.6% of track is changed. So if you look at that, that's only a very small percentage. So track needs to last at least 28 years at that rate of replacement. In some years, it can be lower than that, depending on the funding that's agreed between the government and Network Rail. We're spending more than most of the water companies and more than all the national electricity and gas distribution companies put together. And when you look at it, that's about 21 million pounds every day throughout the 5-year control period. So some big costs there, and clearly something there that there's some big challenges where we're looking for sort of further cost efficiencies as well as increased performance and safety. A bit about the track system from basics. We start at the bottom, the subgrade, what the railway's built on, often natural soil or ground materials, and I'll show a little bit more detail. Underneath that, we have some sort of separation layer, normally often a sand blanket that caps the sort of earth underneath. We then put a layer of ballast on top. The sleepers then sit on the ballast, and the rails then sit on top of the sleepers. The rails are then fixed there. I'll show some examples there. Train wheels, in simple term, fixed axle, 2 big wheels, they sit on the rail. And in many cases, the material and the building, the formation underneath our railway was what was there built originally in Victorian times. Many of our railways, the formation is underneath is over 150 years old. So a big challenge there to run a modern railway on historic foundations. A little bit more, the rails, a lot of different sections, different steel, different materials, but quite a high performance steel required to survive the duties in service. That sits on a rail pad, which provides a degree of resilience and reduces wear. They sit on sleepers, predominantly concrete used now, where the rails sit directly on the pad on the sleeper. There is also innovation with an undersleeper pad now that is starting to be used to reduce the damage between the concrete sleeper and the ballast underneath. But sleepers also come as timber, and more recently we're using recycled composite materials, predominantly recycled high density polyethylene as a replacement for timber, and those are these examples there. On top of the fastening system, we often refer to clips. They hold the rail to the sleeper, and they have various insulating plastic material to link or stop electrical contact between the two. And in some cases, different designs. This is a more modern design, a fast clip installation where the clip remains captive, can be withdrawn to allow the rail to be removed and then re-pushed back into engaged against the rail, and that holds the rail from lateral forces, keeps it longitudinally and fixes it to the sleeper. And there's an example there with the clip installed and the different insulator there. You can just see the pad underneath the rail, which sits between the rail and the sleeper. Also, we may use base plates in certain situations on things like timber and composite sleepers, where there is a base plate there between the rail and the sleeper, and that's bolted in position, or could be used in specific locations where we want to engineer a particular stiffness or a particular resilience to the track. Ideally, we'd all have brand new railways built on a nice concrete base, laid out absolutely perfectly, with very little formation, settlement, and very good understanding of what's beneath the railway. Most of our main lines weren't built, and these are examples of construction. I believe this is on West Coast Main Line originally, but a lot of the materials there were simply removed from cuttings and tunnels, piled up and dumped as embankments without any real engineering design there, and that was crudely consolidated. But in most cases, that often forms the formation of our modern railway. So a big challenge there, where it's not all engineered materials, it was using what was available at the time to construct the original railway. A bit about how we look at our track. Track's made up of a large amount of different duties, different sections, different speeds. So we divide it up for the inspection and maintenance purposes. We divide it up into 7 categories. So we have the top right-hand corner of the graph, which is our highest speed, highest tonnage railways, and then drops down in sections, and each one of these has a different track category. As you get down to the low track category, they're low speed, very low tonnage, but we use that to classify the track to enable us to plan things like inspection and maintenance intervals, where track in the top right-hand corner will perhaps degrade much quicker than track in the bottom left-hand corner. So we use that to categorize the track. We carry some big tonnages. If you look at track category 1A, our highest speed, highest tonnage, that's carrying about 41 million tons a year on average. And then as you work your way down, you'll see these are the different track categories: track category 1, 2, 3, 4, 5, and 6. 6 carrying a relatively small quantity of tonnage, so only 500,000 tons. So the railway quite complex in that the duties, the service conditions are very different from one piece of the railway to another. So we use this subdivision. And then a quick illustration: it's not all track category 1A. There's a large proportion still in categories 3, 4 and 5. These are the kilometres in each section. A bit about rail defects and damage. The track conditions are harsh and the rail is a very heavily loaded component even under normal surface. Excuse me. A lot of people I came from originally a design. I did a lot of work on structural design of bridges, and you would put that together with components which had an infinite fatigue life you were confident would last 150 years. Rail is quite a challenge. It's installed. Often we know that it has a limited service life, and it may result in a failure in as little as a few years in the extreme cases. So quite a challenging asset to manage, in that we are installing new rail with the knowledge that because of the service conditions it will develop defects, damage, which we need to manage, and we know it has a finite life. Unfortunately, the other thing with track is it rarely fails safe. So if we have something like a broken rail or the rail becomes displaced, it doesn't necessarily stop everything. We don't necessarily know, and unfortunately, it's often a driver, a train or a rough ride report, a bump, something like that detected, which is our first point of identification. So quite a challenge. Broken rails also grab the headlines. They're very visible and have caused a number of incidents in the past. And rails, we need to continuously repair and replace them before they fail, or we need to make sure they're able to meet operational needs. We don't have to apply speed restrictions. So we carry out quite detailed planned inspection, a maintenance and renewals program to renew the track as required. So a little bit about the wheel rail interface and what Mark was going to talk to. So I've combined the two together. Our rails, typically for modern rails, two rails, 1435 millimeters apart. They're inclined at an angle of 1 in 20, and they're inclined to keep the forces direct through the middle of the rail. So the rail will provide a vertical force, but also some force out laterally. So to counter that, the rails are inclined. The wheels are set at a nominal back-to-back distance, so they're a fixed distance apart on a fixed axle. And the wheels are designed to run, not that they're tight against the rails at all times. There is a clearance between the two, so there's approximately 8 millimeters clearance either side, but the wheels are conical, and you can see the shape of the wheel, and that is encouraging the vehicles to steer, to follow between the rails rather than run against the rails, which would cause a large amount of wear. If you look at what's happening on straight track, there will be a gap between the wheel and the rail, and the cones on the wheel and the shape of the rail will enable them to steer in a straight line without touching the sides of the track at all. As you go into a curve, that would be a right-hand curve, the wheels will move to the outside of the track, the contact position moves across, and that increases the diameter of the wheel slightly to enable it to steer around the high rail of a curve. And again, the opposite to that, in a left-hand curve, it will displace out towards the side, and on tighter curves, the flange will come into contact with the side of the rail, where you get increased wear. Surface damage, and that's really caused by some of these forces between the wheel and the rail. They're our most common cause of defects through things like RCF, which was rolling contact fatigue. It's effectively fatigue damage of constant cycling of wheels over the rail, or squats, which are a localized condition, also can caused by fatigue damage there on the surface of the rail, which leads to cracks that generate or propagate and will eventually, if not managed, cause a broken rail. If you look at the wheel on the rail, that's a typical position of a wheel on the rail. That contact patch is about the size of a 5p piece, so about 250 square millimeters. Yet that wheel, a static load could be as much as 125 kilonewtons, something like 12.5 tons. And the forces just in the straight contact with it sitting stationary are getting close to the yield strength of the steel. So even though rails are considerably stronger than normal structural steel, the forces that are applied to them are very high. And once you start rolling the train, any irregularities, roughness, then amplifies those forces. So you get very high contact stresses through those points. And it's not just vertical force. The train is trying to accelerate and brake at times, and that applies longitudinal forces, but it also has to steer around curves, for instance, and because it's a fixed axle, there's a degree of slippage there, very high longitudinal and lateral forces, particularly in curves. And it's something, if we don't manage them, that will lead to defects and eventually broken rails if the defects aren't removed in time. So a little bit about RCF damage. This is a section through the rail looking at the structure, and you can see the structure has been very deformed on the surface, and it's effectively all being dragged back. So the direction of travel will tend to pull the material back at the surface. So the steel is actually deformed physically, plastically deformed, and eventually that builds up sufficient strain that there's cracks start to appear at the surface. And a little bit of an example here, this is a bogie underneath the train, so the set of wheels that fix underneath the train. This is going around a curve, traveling from left to right. The vehicle isn't always able to steer perfectly around the curve, and you get an angle that the wheels form. You get some very high stresses because the wheels aren't able to rotate at different speeds. They're on a fixed axle. That leads to high longitudinal lateral forces, and you can see you get a very large force backwards along the high rail, also a lateral force, but the resultant force across there. And if you model those forces and vector those forces, that corresponds to the surface damage. You can just see the cracks then that occur perpendicular to the combined stresses on the railhead. So something that will develop in particularly in curves. We get some damage on the low rail, but predominantly damage to the high rail. A little bit about this, and I won't go into a lot of details, but this is effectively two vehicles. These are the model positions that show how the axle behaves when it's going around a particular curve. You can see a subtle difference here. So it's not just the rail. You can imagine these are two bodies that roll against each other. Even a slight change in the wheel profile. So this is a P1 wheel as new. This is a P8 wheel, which is effectively very much like a P1 wheel. This is the profile that's put on the train. And the slight change there will change how the vehicle steers and how it behaves. So it's a very subtle interface with a lot of forces acting on it. If you look at it in a slightly different way, the wheels are conical, and ideally when they're new, everything is running in a straight line. You'll get contact pretty much in the middle of the rail with quite low conicity. But as things get more worn and the wheel set moves towards the rail in a curve, then the contact moves across the rail. You get much higher conicity, leading to larger forces. So quite a difficult one to manage. And it's something, certainly I came as a structural engineer originally, material scientist, hadn't quite appreciated just how high the forces were between the wheel and the rail when running trains, particularly in curves. And a quote from Alan Wickens, who you may know in history, he was heavily involved, was a specialist vehicle dynamics expert, but was heavily involved with the original advanced passenger train in the UK. And his comment there, I think one that stands out, it's one of the most complex dynamic systems in engineering, and the interaction between wheel and rail involves both complex geometry of the wheel tread and the rail head, and there are many non-linear variables. So a significant challenge there in how we manage the track in that situation. A little bit more about damage caused by about the forces. So I talked about the longitudinal forces. You can actually see them sometimes in curves. Here's examples where the sleepers have actually been dragged through the ballast. So the sleepers should lie perpendicular and was originally installed, but many passages of trains will actually drag the surface, and that high forces on the surface of the rail, they lead down into the sleepers, and you can see how the sleepers then have become angled as the rails are dragged backwards by the forces in curves. So they're not small forces, very big forces in that situation. And that leads to our sort of rolling contact fatigue type damage and various sorts. Starts as very, very small cracks, but will then propagate into the rail and eventually lead to rail failures. So if you look at some of the damage, we also get damage on the low rail, tends to be in the middle of the rail. And whilst not such a big threat from causing the rails to break, makes life difficult if you're trying to inspect the rail, the surface is damaged, and using things like ultrasound, we can't get signals reliably into the rail, and we'll need to change the rail or reprofile the rail to maintain the ultrasonic testing capability. As a little example, this is a section of rail, very light RCF viewed from the top of it, and you can see when you break the section open, the very small cracks starting at a shallow angle near the surface. They will then grow, and they grow both down into the rail and across the rail. And when they reach a distance about 5 millimeters down, they will often turn down into the cross section. And there we get a big defect there. You can see the darkened area. And that is a result of the rolling contact fatigue, but that then potentially causes a broken rail. And back in 2000, just after I joined the company, a broken rail here was Hatfield on the 17th of October 2000, which resulted in a high-speed train derail that was on its way from King's Cross to Leeds, and that derailed, went out across the curve, and 4 people were killed there when the train hit an overhead line stanchion in the cess where it had come away from the track, moved across, and then collided with the infrastructure. The train derailed at this point. Part of the train continued on, the back part separated away, but in the central section you can see the damage to the carriage where it collided with the overhead line gantry, and that cut open the buffet car on the carriage and tragically killed 4 people. That was the original defect, a very large defect, and one where certainly the challenge now is how we prevent a defect growing to that size, how we remove it well before it's got to that point, and the rail is then at risk of failure. Excuse me. We've had some success. This is long-term broken rail numbers, and traditionally this is over about 60 years now. It ran at about 750 broken rails a year, but we did a lot of work post Hatfield, and I'll show a little bit about that to try and reduce those numbers down. And currently we run at about 125, perhaps down to 100 breaks a year, perhaps a little less than that now, but still striving to look for further reductions. Whilst not every broken rail causes a derailment, there is always a risk with something like that where the train could derail. Some of the things we've done, and it's more an example slide, I'm not going to go through them in detail, just to really make the point that this was not something where there's an easy quick win. There was a lot of activity, a lot of work through research, through changes in inspection, through railhead treatment, through changes in materials. So quite a complex exercise to try and look at how we reduce those numbers down, and certainly some big things that made a difference. You could see numbers came down quite quickly. Our challenges going forward is reducing this further, where some of those easy challenges or some of the bigger reductions were already being done. So reducing it further becomes a bigger challenge, but clearly something we need to do to manage risk. And it's not just a few broken rails. We've cut the numbers down, but this was a broken rail in October 2014. It was a low rail of a curve. The rail broke up, it split along the length of it, and that derailed a freight train. So it starts as a crack in the middle of the rail, very difficult to see, doesn't extend to the outside, but that grows, and eventually it lets the rail split in two. The head breaks off away, and that then resulted in the train derailment. Similarly, in 2014, a broken rail here derailed a freight train on a set of switch and crossing, a small defect in the foot of the rail at this point. That caused the rail to break, and once that section of rail broke out, that allowed the train to derail. It's quite complex. We also have a lot of external challenges. So whilst we can manage and inspect the track and rail and look at the condition of the rail, we're also subject to the impact forces from vehicles. And this was an example in 2017, just over 4 years ago. where a vehicle wheel jammed and then released whilst it was in transit, and that created a very big wheel flat on the wheel, and that, as it rolled round, effectively acted like a hammer blow, causing 10 broken rails in a relatively short section of track. So a big challenge there, in that we can control the rail, but we can't always control the forces that act on the rail. So looking at how we better manage those, how we manage the wheels, it's important to manage the interface between the two. It's a system, it's not just maintaining the track. A bit about broken rail causes. Main cause are small defects in the foot of the rail still, which result in failure. So we're working on technology and systems to highlight areas at risk of this type of failure. Perhaps more unusually, our second most common cause this last year was a break at a particular weld between the switches and the crossings. And where we weld that, it's a particular complex weld between two different metals, and we use an insert piece in the weld. And if there's a defect, or perhaps from manufacturer, that then subsequently breaks. So quite a bit of work now, and we're looking at carefully as to how we remove those at source and improve the welding procedures, but also how we manage any existing welds that are out there. We've got 19,000 sets of S&C, many of which have got this type of weld in that location. So some big challenges, but you can see a lot of other varied reasons that cause rails to break. So it's quite a challenge if you're looking to reduce them further. Yes, tackling these is obvious. That's the one to get the numbers down, but that's quite a challenge when the defect is very small in the foot of the rail. And it's not just about broken rails. I mentioned about defects. We need to remove defects and manage the rail through inspection and maintenance. This is just a chart for the last 5 years, but you can see on average we're removing about 32,000 defects each year. So that's about 1 defect every kilometre of track each year. So it's a massive task to manage those. We've got to find them, inspect them, plan their removal, and then replace the rail at these locations. So it's a very big challenge there, with something where new defects are constantly being found. We're planning their removal, removing them, and the cycle continues. And it's not just broken rails in colder weather, but if it's too hot, this is an example of a buckle. So the rails have got very hot, they expand in the heat, and if they are not properly constrained, they will buckle. And there's an example there, which unfortunately in that situation, if we have a buckle that's severe, then equally that can cause the train to derail. An example of a freight train that derailed during a particularly hot summer in 2003. If you look at the hot weather, it's something that's quite a challenge. So we've got to think about this. The rails, the steel rails, expand quite significantly as they heat up. And these are plots in 2018. The top red line is temperature, and the bottom line is the drop in performance. So this is where we aren't able to run the service reliably. And you can see the first time it gets hot in the year, a big impact potentially. Temperatures then increase, and then we have another significant rise and a hot spell and a big impact on performance. So again, it's perhaps a bit different 2019. It wasn't prolonged hot heat that we had in 2018, but again, you can see the very clear high temperatures and poor performance go hand in hand. So a big challenge how we manage that, particularly as the rails, when they're sitting out and the sunlight, can reach temperatures up to 60 degrees centigrade. So managing that through correct rail management, through stressing the rails, making sure it's adequately restrained laterally, the sleepers are embedded in the ballast successfully, is critical in that situation. And a few other couple of examples. It's not just broken rails. This was an incident in 2002 at Potter's Bar. We had a set of points just before the station at this position, which some fastenings came undone on, and part of the equipment that holds the rails together separated. That allowed the rail to move uncontrolled, and part of the train then took a diverging route that caused it to effectively barrel roll, embedded itself under the platform there. So a big challenge there, but that was through one small broken bar and some loose nuts that came undone, resulted in a derailment. And then similarly at Lambrig in February 2007, a set of points here. You can see that's set to go round this direction, but the bracket holding them together failed and the nuts came undone. You can just see the washers and bits in the background. That allowed that rail to move across under the train. Part of the train then went round this diverging route. The rest of the train continued on the normal route, and that then again caused a Pendolino to derail on an embankment. That was the leading car. The rest of the train and the carriages there, fortunately, it could have been a lot worse, but again, someone tragically killed in that situation. So once the train leaves the track, there's an enormous amount of energy and a lot of damage done. So really, as a conclusion, track really doesn't look after itself and neglect it at your peril. And the importance we really of monitoring and understanding the condition of the track, particularly as it becomes older and more worn. And many of our controls against broken rails, the management of defects, they're all underpinned by inspections carried out at set frequencies. If we don't identify a defect, then most of our subsequent controls are less effective. We aren't able to manage it. So finding the defect, understanding it, sizing it, and then managing it is critical in that situation. There's a great deal of effort and expenditure into monitoring rail condition and repairing or replacing the components at the right time scale. So it's not just a stick it in, forget about it. It's very much a constant exercise to maintain the rail in a safe condition. And then things like assurance and compliance become critical then in controlling and managing the risk of track in that situation. And yeah, as an example there, that was Hatfield. Unfortunately, 4 people were killed, but one broken rail that pretty much fundamentally changed an industry back in 2000. So certainly led perhaps part to the demise of rail track and a huge change in the way engineering was managed within the railway industry. So a challenge there, but sort of lessons that we shouldn't forget in the future. I think, thank you very much, and apologies Mark wasn't able to join with that, but a bit of combination together. So hopefully that gave you a bit of a flavour of track. And it's not simple, it's quite a challenge, but that challenge makes it interesting. Thank you, everyone.
That's great. Thanks so much, Brian. That was really, really interesting. And again, really drives home how much attention needs to be put on safety across the railway. And also reminds us all how much goes into the track. Every time I hear about it, I find about 50 new things that go into it. So really interesting. Thank you so much. So without further ado, we'll hand over to our next speaker, which is Jaden Mannion. So over to you, Jaden.
Right, good evening everybody, thank you very much. I'm going to be talking to you today about switches and crossings and reliability and developments we've done in SNC recently. Next slide please. So first things first, who am I? I am a mechanical engineer with a bachelor's in engineering, got my degree at the University of Birmingham and I graduated in 2016. So after graduating, I started working Network Rail. So I've got roughly 6 years of experience. So that puts me in a position where I'm not quite new to the railway, but I'm not one of the most experienced that you get. So we tend to have loads of people on the railway with 30 or 40 years of experience. It's really quite impressive. When I started at Network Rail, I joined the graduate scheme, as a couple of other panel members will have done as well. So I've had the opportunity to have posts inside of maintenance, asset management. I also did some work on standards and policy management. And for the last 3 or so years, I have been in the technical authority switches and crossings team. And that's given me an opportunity to do quite a lot of stuff in regards to research and development. So one of the big things I'm working on right now is modular S&C and trying to introduce a new product to deal with some of the issues we've got. And a lot of data analysis on faults and failures so we can understand trends and try and look at where we can try and improve reliability. Next slide, please. So, can we go back? Yeah, there we are. So S&C. S&C is how you change from one track to another track. It sounds really simple, but there are a lot of forces involved in essentially trying to bend really, really massive, heavy pieces of steel so it allows a track to switch. also has a lot of moving components. Permanent Way Institute makes it sound like track is always stiff and unmoving, but S&C doesn't quite work like that. In addition, S&C is a large system. It's not just track and civils and what is underneath the railway, underneath the rail that's important. You've got a lot of points operating equipment, which includes all of electrical systems, and S&C is the combination of all of that. In addition to that, when you're trying to move a train from one track to another, where those line cross on those diagrams, you have to include space for the wheels to actually be able to move. And you can be off by a few millimeters and end up with a derailment like Brian was showing you earlier on. S&C also will need to be maintained very frequently because there's a lot of moving components, there's a lot of wear. In addition to that, you can get a lot of damage. So because of the massive amounts of lateral forces, and as Brian was mentioning earlier, those are all concentrated into a 5p piece, that gives massive opportunities for wear and damage. And plus, because S&C, these are the places where you switch track, if you have to clamp one of these out of use, then that will have a big reduction in the amount of capacity that you can have. So you need to find alternate pathways for trains to travel, or you need to cancel services altogether. And if you don't do this, well, there's nowhere for the trains to actually go. Can we go on to, nope, one more thing. So S&C also has a really big carbon footprint at Network Rail. Reason being, there is a lot of steel and a lot of concrete involved inside of this. And if we don't maintain these reliably and they get damaged and we have to continually replace them, we are inputting lots and lots of carbon emissions into S&C. So there's one of the areas of Network Rail which has massive, massive implications on carbon emissions. Next slide, please. So we have a lot of different types of S&C and a lot of different types of rail. So you may have heard terms like bullet rail, 56 or SEN 60 rail. So what I want to talk to you about today is NR60 Mark II. So NR60 was introduced because it has a similar geometry to a lot of what currently exists. The other SEN 60 rail type, which is NR60 Mark I, has a different geometry to what currently exists. They have different crossing angles, different lengths. And the reason we wanted to introduce something which was very similar to what currently exists is because we need to take into consideration the footprint. So if you take a look at that image right there, right at the far end, you can see there's off track and there's greenery there. So if we were to introduce a piece of S&C that requires you to move into that and cut into that, that can be very expensive. And in a lot of cases, we don't always own the asset, which we would then need to reduce. On top of this, we need to consider, or one of the things we wanted to improve was the contact area and the rail profile. So by managing this rail profile, we can make sure that the wheels are following the best contact area to cause as little damage to the S&C as possible. And by going from a SEN 56, which is a smaller and lighter rail, we can increase the robustness of it and allow us to maintain it for longer and replace it less. Can we go to the next slide, please? So what are the changes and why? The wheel rail interface has been changed. So again, this reduces the impact loading. So we get a lot of damage around crossing noses, and we wanted to focus on trying to reduce that. And by changing the area that the wheels will contact, we can do that. We also use a different piece of points operating equipment. POE is what drives the switch, so which is what drives the rails and allows you to move from one track to another. And I'll go through a little bit more on that a little bit later. And by introducing a crossing footprint that is more robust, we get additional life out of it, and increasing the life of the crossings reduces the amount of maintenance you need to do with it and allows you to save time and money and focus that in other areas. Next slide, please. So one of the other improvements of NR60 Mark II is it has increased thermal resilience. So we may think that we don't get massive temperature extremes here in the UK, but even going from 30 degrees to -5 or even -10 degrees, the amount of stress that can be in the roller at those temperatures varies wildly. And as we all know, metal expands and contracts at different temperatures. So by designing in additional thermal resilience in NR60 Mark II, we can combat those stresses much more effectively. And by having reduced rail wear, we get longer life out of what currently exists. Now, NR60 Mark II was piloted and tested and developed in 2016 and 17, roughly 5 years ago. And since then, we have installed 50 point ends. I'm happy to be able to say that we've got no attributable service affecting failures at the moment, which means the mean time between service affecting failures is infinity, and hopefully it stays like that for a while. We have had faults and failures before, but none of these have affected the service and have not been attributed as the cause to any cancellations or delays so far, which is a big benefit. Next slide, please. Next, I'd like to talk to you about the in-bearer clamp lock system. So we are on the third iteration of this system. So one of the things we do is when we are trying to increase reliability, we look at the most common failure modes in an existing design, and we try to look at and understand what these are and redesign to get rid of these. So by looking at what the current fault mechanisms are, we can make it easier to set up, we can reduce issues with human error in trying to set it up and put it in place, and we can increase reliability. Next slide, please. Next slide, please. So what have we actually done? So one of the things we've done is we used to have 2 single acting rams. By combining those into a single double acting ram, we've removed one component, which reduces one potential area for failure, and it will also take time across setup, and we're always trying to find savings in installation times. We've changed the drive lock method. We've gone to a threaded adjustment lug rather than packing pieces, which is another easier, faster way to set up. And in that image there, those are the Mark II cam design and the new cam design. We've gone to a design which should reduce the transmission of vibration, which will reduce overall wear and extend the life of that component. And we've gone to a spherical bearing on a lock and arm detector. And this should prevent something which is called the woodpecker effect, which is a continual hitting of it. Next slide, please. So the image on the last slide showed you could see that the surface finish of those 2 components were very different. By introducing a hardened coating, we've reduced the wear rate of this, so it's something we won't need to go in and replace or go in and fix as often. Redesigning that cam so it's less prone to vibration, it will reduce damage to components. And we've introduced a roller on hollow bearer. So what this will do is it will reduce toe drag, and it will make it easier for the points operating equipment to move the switches from one road to another, and that will increase the overall switch performance. And we can now carry out the detection from the 4-foot rather than the 6-foot, which we will call a safety improvement, and there's no lubrication required on one of the pins. By going to a dry bearing interface, this will reduce the buildup of contaminants, and it's not something we need to go out and remove and maintain over time. Next slide, please. So what does this increase in reliability actually lead to? So that picture there shows that that will be a junction of S&C. It looks as if 4 routes are going towards that one junction. And by increasing the reliability of that, we're making sure that the capacity in the railway, which allows you to use all 4 of those directions, remains available. And it is also gives you a more comfortable ride for passengers. So Brian was talking about rough rides earlier, and S&C is a common place where you can get rough rides, because as the wheels of the train are going from one road to another, it is not difficult for that to create a rough ride if the contact area isn't done correctly. So if you've ever been on a commuter trains in some areas early in the morning, sometimes you get commuters will all lift their coffee cups at the exact same time. And the reason they'll do this is because they've been over that a lot of times, and they'll have an idea of where some of the rough rides exist if it's been in there for too long. And what we're trying to do is we're trying to reduce that, because that increases the amount of damage on the S&C. Giving an asset which has greater reliability means you can spend more time and money on other more critical areas, and it also leads you to have greater route reliability. And by increasing the opportunity you have to maintain an asset, it delays the amount of time required until you need to go in and replace that asset as well. And it also gives you more time to inspect the track and find areas that you would need to go and maintain. Next slide, please. So the last thing we'll talk about is the S&C, or the carbon reduction aspect. So we are using a bigger, thicker, more robust section of rail with NR60 Mark II than we have with the NR56 or 756 rail. So you might think that because a lot of the carbon emissions will come from that steel, we've actually increased. But by having a more robust rail and something that will last longer and you can maintain more, you've actually reduced the carbon emissions throughout the life cycle. So focusing on that reduction in carbon early on in the life cycle leads to a reduction in the whole life cost. In addition to that, if we've got something that's more reliable, we will not have, or we will not need to use strategic spares as often as we do. So what we do is, because a lot of these S&C junctions can be very important and critical to the running of the rail, once we've put it in, we'll also put in an order for a strategic spare. It can take several weeks or even several months for a new crossing to be cast. So by having a strategic spare, we can reduce that time period. But if we don't need to use that, we don't need to continually keep ordering to make sure we've got a strategic spare, and that will reduce the overall emissions in the S&C that way. I think that is my last slide. Thank you very much.
That's great. Thank you so much, Jaden. And yeah, again, really interesting presentation. I think the resilience point's probably quite topical, seeing as COP26 currently going on. So yeah, it's really great. And we'll come back to you later with the Q&A. Thank you. So our next speaker, I think, is Richard Stainton. So I'll hand over to Richard now, who's going to talk about electrification. So over to you, Richard.
Okay. Just bring in your slides. Thank you very much. If you want me to share this end, Jacob, oh, right, you've got them. Cheers. Sorry, just bear with me a sec. I think it's just because they're so large. You should be good to go now. Okay, great. Thanks very much. So, thanks so much for the opportunity to speak tonight. Maybe just give a little bit of background about myself, as the other speakers have. My name is Richard Stainton. I joined as a graduate trainee, like a number of other guests tonight. That was 20 odd years ago, and similar to many other people, I've spent time in maintenance, in asset management, in route teams, and on major projects, and in the design teams that NetWorld have, as well as the centre, or HQ, as most people will know it. So it has a broad experience of electrification. My current job is focused in 3 areas: research and development, standards, in particular NetWorld standards, industry standards, and European standards, and also technical support, so providing support to projects and regions with interesting technical problems. So and that's basically one of the talks, how the talk I gave tonight started off, and it has now merged into all 3 of those areas that I work in. So the talk tonight is about avoiding bridge reconstruction, or basically how to avoid electrification projects look like the picture you can see in front of you. That's a picture of Great Western, and as we installed electrification on the Great Western route, we had to rebuild an awful lot of bridges, far more than we initially anticipated when we started the Great Western project. Next slide, please. And basically, the reason for that is the electrical clearances. So you can see there, that's a existing rolling stock operating underneath a bridge, and there's very little space between the rolling stock and the bridge for electrification and the pantograph. So if you go to the next slide, please. It has a big impact on costs. So over the last control period, so control period 5, we've installed over 1,000 kilometres of electrification. Each electrification project was different and for many different reasons, but by and large, you can split the cost of those electrification projects into thirds. So about a third of an electrification project was spent on the overhead line. So the foundations of the masts, the master steelwork, and the wiring and the commission associated with that. And that's labour, plant, materials. So that's not just the material cost. The material cost is actually quite low, about 5% of an overall electrification project. Another third is spent on all the other bits and bobs associated with electrification. So signalling immunisation to allow electric trains to operate, enhancing the fencing because we've got quieter trains and possibly higher line speeds, devegetation to provide clearance between the vegetation and electrification, and other costs such as operator compensation and connections to the national grid for traction power. And the last third is spent on route clearance, so in lowering track and tunnels, modifying the station canopies on platforms, and either rebuilding bridges or lowering the track to accommodate the electrification system. And every so often we get to bridge that just where it's not possible to use one of the standard solutions. So if we go to the next slide. So this is Cardiff intersection bridge, where we have the lines from Paddington to Cardiff Central going from across the screen. The Paddington's on the 200 kilometres to the right, and Cardiff just 400 metres to the left of the screen. And going north-south is the Valley lines going for the Transport for Wales network, which go into Cardiff Central, up to Cardiff Queen Street and into the valleys, and go south to Cardiff Bay, if anybody knows it. Now, what's probably not immediately visible on the screen there is there's actually a canal going from the G of the bridge, running directly underneath the Great Western Main Line, and then goes under the bridge itself into the docks. And that canal feeds the docks, which is a site of scientific interest. It also acts as the main firefighting reservoir for a road tunnel between Cardiff and Newport. So a particularly challenging site. And if you go to the next couple of slides, you can see just how low the bridge is, and that we have a number of piers in the 10-foot supporting the bridge, and there's a picture of the canal, and you can see just how close the canal water level is to the rail level. There's very little room for manoeuvre. Replacing the bridge was estimated to be about £40 million due to the congested network, congested site. The alternative was looked at was trying to divert the canal, but that would have required piping the canal through the centre of Cardiff to ensure that the water flow was continuous while we undertook the construction work. So either way, it's a big issue. So Jacob did a great job. Next slide would be great. And just to give you an background of the challenges we have when we put electrification into the bridge, there are a number of different clearances we are trying to manage here. And these are the typical clearances that we have used for electrification. So a number of clearances that are there required when when there isn't a train present, and obviously when a train is present, the pantograph pushes up on the contact wire, which means we have even less space to work with and more opportunity to flash over, not just from the uplifted contact wire, but also the pantograph onto the bridge, which I think is the next slide, Jacob, or the slide after that. I think there's two more here. Perfect. So yeah, so that gives you some idea of the hazards we're working with. If we look at our bow tie, which is probably a good way of looking at the risks associated with electrification underneath a bridge, we've got the yellow box, which is the hazardous item we're trying to control, in which case we've got some overhead line or OCL energized at 25,000 volts. And the red circle in the middle is the hazardous event we're trying to prevent, which is a flashover. On the left-hand side, we've got three blue boxes which show the threat that we're trying to control. So the flashover could occur due to either a voltage transient or voltage spike, the clearance being compromised by debris or wildlife, or the clearance being compromised by the pantograph uplift. And should we have a flashover, on the right-hand side, we've got two consequences, which is damage to the bridge or damage to the OCL. So this is how we try to communicate the risk assessment that we carried out at this particular bridge. So if we go on to the next slide, you can see how we started to address this. So with voltage transients can occur just due to switching, whether it's with the overline isolators or disconnectors, or the circuit breakers in the substation. Also can occur with arcing between the pantograph and the contact wire, or even just the switching frequencies of the modern rolling stock. So the transients occur by a large variety of means. I'm not going to go into all the different types of transient events tonight, but when we are testing the electrical installation properties of the electrification equipment, we test to a 200,000 kilovolt system transient, which is the orange trace that you can see on the chart there. That's a big ask when we start looking at the electrical clearances we're trying to get down to. So the first task was trying to absorb that energy so that we could deal with the 200,000 kilovolt test with in a different way. So we've done that by using a surge arrestor, which absorbs the energy of the transient, and the resultant of that is a transient waveform shown by the green trace on the chart here. So if you move on to the next slide, Jacob, you can see how we are installing surge arresters. So they're installed on 2 per road, either side of the bridge face. And the surge arrestor just looks like another insulator. It's installed on the mast and it's connected to the catenary. It's quite an inert object. It just sits there absorbing transients all day. And I guess if in the very unlikely event it got firmly overloaded, like a lightning strike, for example, a direct lightning strike, an example, then the earth connection at the bottom would drop out with an expulsion fuse at the bottom of the surge arrestor, and the surge arrestor would still sit there, the electrification would still be energized, but the protection wouldn't be provided by the surge arrestor until we went and changed the surge arrestor out. For that reason, we provide 2 surge arresters, so we have an element of redundancy on the system. So applying surge arresters allows us to manage the transient voltages, and we are fortunate that we're not just alone in trying to solve this problem at the moment. We are a couple of years behind the Danish railways, who've got the same problem. And if you go to the next slide, we can see how the Danish railways have installed surge arresters on their electrification system. You can picture there, courtesy of Google Earth. So, and we're going to the next slide. You can see that when we look at the bow tie diagram, that if we and next slide again, you can see if we install surge arresters, we act as a barrier against voltage transients. We've also looked at the clearance compromise of pantograph uplift. So where we are different from Denmark and other railways is that we then took all the electrification equipment to a high voltage laboratory. In this case, we use the University of Southampton's high voltage laboratory. You can see various pictures of various test equipment on the right-hand side and the environmental chamber on the top right. On the left-hand side, you can see some bridge surface samples. So you can see a brick and a concrete sample that we've had that have been soaking in what's termed a paddling pool, but they were soaked in submerged in water for over 48 hours before we undertook any electrical testing. And at the bottom picture there, you can see a steel plate. So we're using samples of all the different construction types we have with bridges. The steel plate is representative of the Cardiff intersection bridge. The white residue you can see on that photograph is a pollution mix that we've applied to the steel plate after we applied the insulated coating. So it's a steel plate with an insulated coating and a pollution mix applied on top of that to really test the setup we've got in that configuration. And if you look at the next slide, you can start seeing some of the test results we've got. So this is a photograph of testing at the University of Southampton. This shows I think you've got a brick obviously at the bottom right, then the concrete sample just above it, and the steel sample to the left. The concrete and brick are actually upside down purely because logistically it's very difficult to fit a concrete and steel sample in a high voltage test chamber the way you'd expect it to be on the railway, but luckily electricity doesn't respect gravity, so we can carry out those tests upside down. And you will have noticed that all these photographs are showing a flashover. That's because the photographs are a lot more interesting, basically. The testing was carried out in 5mm increments, so if you can imagine that if that gap was 5mm greater, then we would be avoiding that flashover event. So that's an example of the testing we've carried out with bridge arms. And if you move on to the next slide, please, you should see similar examples of testing with contact wire. So we've just supported the contact wire directly above the bridge samples, and just bent the ends of those contact wires to avoid any electrical stress rises that could occur. It was all modelled first to ensure that we had sufficient radius to avoid any electrical stress rises before we carried out the testing. On the right hand side there, you can see the contact wire has a contact wire cover installed, and that's another one of the OLE components that we tested on top of the and you can also see the insulated bridge arm support there holding those assemblies together. So with all that combined, we could start to see how close we could get to the bridge surface. So if you move on to the next slide, please. This is an example of the test results. So along the top there, you've got the clearances from 70mm down to 0. And for the testing to be declared a success, you need to test both a positive impulse and a negative impulse. And each one of those impulse tests need to be carried out 3 times before we can declare it a success. So you can see with just a contact wire, we failed. At the top there, with a surge arrestor, we could get down to 30mm, but we had a flashover at 20mm. The contact wire cover in the dry didn't make much difference, but when we added the insulated coating applied to the bridge surface as well, we could get down to 0mm, so it was actually physically touching. We tried it again with the wet. This is Cardiff. So we had a 60mm and with just a surge arrestor. Surge arrestor and the contact wire cover got down to 40mm, and with the insulated coating as well, we got down to 20mm. So from the 270mm we started with, we managed to get down to 20mm by doing this series of tests, which was a significant improvement. And if we go into the next slide, please. But that's not it. We also had to look at the uplift of the contact wire as the vehicle passes underneath a bridge. So we have used digital imaging cameras at a number of locations throughout the country. So a variety of overline equipment, a variety of train types, pantograph types, line speed, etc., and a variety of maintenance procedures. And that's allowed us to get a really good understanding of the variety of uplift conditions that we can reasonably expect underneath bridges. So if you go to the next slide, please, you can see a trace that this equipment's recorded. So you can see, in this case, it was a train with 2 pantographs passing, and the uplift was around 22 millimeters. So going to the next slide, you will see the overall results. So we've got over 1,000 measurements, and you can see rather satisfyingly that the measurements we took, the mean of a 20 millimeters is what our dynamic modelling predicted beforehand. So that was definitely a bonus. But it also shows the range associated with running a railway in real life rather than a computer model. So we're now using a mean plus 3 standard deviations, so a 99.9% chance of a probability. So it's about 43 millimeters of uplift value we used for this particular bridge and all bridges in the future. So this, again, it was a significant reduction to what had been assumed in the past, because historically we'd assumed over 70 to 80 millimeters in restricted areas, even though the modelling was saying it was 20, because we knew that it wasn't representative of all pantograph types, but we've never had the opportunity to measure uplift in this level of detail. So if we go into the next slide, please. And I think, Jacob, you've got to press the button about 8 times now, but you start to see that when we align all these mitigations together, we form strong barriers to prevent the flashover. And in the event we do have a flashover, then we do have mitigation to manage the risk and to avoid damage to the bridge or the overhead line, in the forms that we will bond the bridge to the traction return system, so we've got a low impedance path for the fault current. And we also have a rapid protection systems that detect the short circuit, that manage the resultant voltage rise on the surrounding area or the metalwork to a value that's identified in the European standards. So we can manage the touch potential to a safe level, and by using protection and bonding. We go to the next slide. In this particular bridge in Cardiff, that wasn't enough, so we also had to look at lowering the wire height. So the minimum wire height laid down to group standards is 4165 millimeters, and we carried out another piece of research looking at the electrical clearances between the overhead line and the roof and the pantograph roll. So I'm not going to go into this one in too much detail, but if we go into the next slide, you can see that testing has been carried out with various train roof profiles. So this is we use various gauges for W6A train gauge, W10 and W12, and then we added things like aerials onto the roof of the train to really understand the electrical clearance properties, or rather the clearance required to avoid a flashover. And on the left, you can see the clearance required without a surge arrestor, and on the right, you can see it with a surge arrestor. We also carried out in-service tests. So this is a test we carried out at Scotland on the Paisley Canal. And the bottom right there, you can see a victim plate just positioned just above a bridge arm. And we surge arresters on the next structure along, away from the photograph. The victim plate is mounted on a hinged assembly, so if we had an issue, we could move the victim plate out the way and not disrupt the train service. So given the next page, you can see just how close we mounted the contact wire, or the bridge arm, to the victim plate, so under 50 millimeters. And you can see it's a nice wet Glaswegian evening. And I'm pleased to say that that passed its trial with no flashover events, despite it being that close. And so that gave us confidence to go on with the Cardiff Intersection Bridge. So if we go to the next slide, we've energized Cardiff Intersection Bridge in December 2019, so almost 2 years ago. We've got clearances of, as demonstrated in the laboratory, down to 20 or 30 millimeters plus the uplift. And we haven't had a single trip or flashover, so it's working exactly as we expected to be. It's outperforming what we expected, which is really good news. So, but it's not just bridge clearances we need to look at. If we go into the next slide, the other problem that caused a lot of problems of electrification is electrical clearances. So we have this little man in an EN diagram about how we manage electrical clearances between our standing surface and any live equipment. So you see R equals 3.5 meters. If you press the next slide, you will see that actually when you apply those dimensions to a station platform, and in the UK where we have high platforms and we're trying to get the wire low to go underneath bridges, we end up having with the challenge of trying to maintain those 3.5 meters clearance between the tip of the pantograph and the standing surface of the platform. Now we are able to risk assess this, but the risk assessments were proving challenging, and as you can see in the next slide, we did actually even do a survey of handheld objects held by passengers at stations. So while walking sticks and umbrellas are the usual ones, you can see everything from skis, scooters, skateboards, selfie sticks, and even lightsabers were held when we did a survey of all passengers were carried at station. We didn't really feel like using a lightsaber to do some testing, but we did do some more testing at the university on the next slide. And you can see that we used a copper rod to work out the minimum clearance required between the pantograph and a rod without a surge arrestor. And on the next slide, you can see the difference that the surge arrestor makes in terms of the electrical clearance. It's again a significant reduction. But we thought we could do better than that. So we've carried out another bit of R&D looking at insulated pantograph horns. So if you can go on to the next slide, the majority of all modern pantograph designs have a open horn design, as you can see there. And the white horn, which is lower than the metallic horns, is actually a composite or insulating material that we have machined to replicate the steel horn that would normally be bolted in place. If you go on to the next slide, so we've machined it to fit the existing profile. With aerodynamically, it's neutral, and weight is almost comparable. And then we've carried out an all number of mechanical tests with loadings. It can go with over 1,000 newtons, which is while it's tiny compared to the forces Brian was talking about, it's far more than the forces we'd normally expect to see on the overhead line. And then we've always carried out electrical testing again at University of Southampton, and you can see that we're now able to have well, in the test laboratory we can almost touch the end of the horn, but not that I would want to volunteer to do that myself. But it shows you that electrically we've got that clearance really far down from where we started from, and all that gives us a great. And the insulated pantograph horn trial should start next week in service, and that will allow us to get great opportunities to get an in-service experience of operating the trial, and hopefully in the future we can get that implemented more widely all across the railway. So these are sort of measures that we're looking at to try and reduce the clearances required for electrification. And if we could do that, we can really reduce the cost of electrification. Remember that pie chart from earlier on. So go to the final slide, I think. Yes, so the final slide, I think it's 4 buttons here, Jacob, sorry. Yeah, so to summarize it, by reducing the number of clearances, the amount of clearance work required for electrification, we have simpler consents. We don't need so much planning permission or submissions to English Heritage, etc., to modify the railway. We also reduce track access because we don't need to rebuild so many bridges, which also means we have a reduced impact on neighbours and train operators. And it also reduces not only just the cost, but also the carbon content, because the carbon content of rebuilding bridges is considerable. So if we can retain existing bridges for longer, it reduces the carbon footprint of the embedded carbon footprint of electrification. And all that adds up to, I think the last bit was putting passengers first. So thank you very much.
Thanks so much, Richard. Another really great presentation. And just in the interest of time, we'll go straight on to our next speaker now, who is Gareth Evans. So Gareth, over to you. And then after you've finished, we'll have a few minutes at the end just for questions. No. Gareth.
Thank you, Isabella. Good evening, everybody. Thank you for the opportunity to present tonight. My name is Gareth Evans. I'm the Network Technical Head of Track in the Technical Authority in Network Rail. Essentially, my job involves making sure all of our track engineering standards, the requirements in those standards are, we review our ability to deliver those, we make sure they're up to date in terms of complying with legislation and other aspects of sort of railway governance, assuring the board that people are complying with those standards. I've lost the presentation now.
Sorry, I'm just going to bring your personal one up.
Okay, thanks. And then learning lessons when things don't go quite so well, making sure that our standards and the way we train people and equip people to work on the railway improves, with the lessons we learn from what we term wrong side failures, the kind of things that Brian and Jaden have talked you through for the track infrastructure, for example. My background, I'm a bit less conventional than some of our speakers tonight. I started life in the steel industry, working actually manufacturing steel rails and steel sleepers that were sold to Network Rail and actually railways all around the world. And then I joined Network Rail in 2009. So what I can say to all of you listening tonight is congratulations, you've chosen a fantastic industry to be in. There is so much opportunity to learn, as Kamini said earlier, and so much opportunity to make a difference to not only to the railway, but to the way UK PLC delivers for everyone who lives in this country, and making railway the chosen form of transport. So if you go to the next slide, thanks. So I just wanted to briefly touch on a few of the industry and infrastructure challenges and opportunities. I'll go to safety first. So railways have, and the UK railway has rightly gained a reputation for being one of the safest means of travel. So that's our challenge. We have to maintain that. We've set a high bar. We've got to keep raising the bar. We've also got to make sure not only are our passengers and other railway users safe, but our workforce are as safe as possible. So how do we make sure that we can continue to inspect, maintain and renew our infrastructure, but also minimise the exposure of the people that work in the railway to the hazards that exist, both in terms of trains, plant and equipment, and other sort of environmental effects. This leads us into more and more work being done at night out of the way of timetable trains, but that in itself presents a number of challenges, not only in terms of how we manage safety of that work, but also how do we convince ourselves that we are inspecting the infrastructure to the right standards as we do more work at night. Very topical at the moment, weather, climate change and decarbonisation, and also linking back to safety of people who work on the railway. We are seeing more and more effects of extreme weather and the challenges that poses. Brian touched on trees on the line, again, all driven by storms and more extreme weather effects. Jaden talked about hot weather and the effect on the track and S&C. Again, as we get a warmer climate, we see more extremes of high temperature in the summer. Is our infrastructure resilient enough to those temperatures? And quite clearly linked to that and addressing the root cause of some of this climate change is we need to play our part in the decarbonisation of our industry. How do we limit our carbon footprint? How, where can we make a difference to the national and global effort on this front? And then right-hand side, really, in terms of train performance and capacity and efficiency, as Brian mentioned, we spend £21 million a day keeping our railway running. After COVID, we've seen quite a shift in the way passengers use the railway. So we're still only at about 50% of capacity for commuting. But leisure use has returned almost back to its pre-COVID levels. So is the kind of future of the railway a slightly different picture to before COVID? Perhaps it will be more of a system used for leisure travel, and the emphasis will move to making sure the system is reliable over weekends and evenings and at night. Who knows? with more freight potentially as well. So if we move on, thanks, Jacob. So how might we respond to some of these challenges? I wanted to give you kind of a high-level example and go into some bits of technology. So there is a rail industry technical strategy. So all of the organisations throughout the rail industry have got together and agreed on these 5 key goals. You can see there, from easy to use for all through to data driven. So these are the high-level themes which a more detailed technical strategy has been fleshed out beneath. You can see on the top right there, it's endorsed by, in Network Rail, our boss, Andrew Haynes. He has signed up to working with the wider industry to achieve these goals, and all designed for the 4 outcomes you can see below. So we want to have happier travellers, happier passengers and customers, both train passenger operators and freight operators, as well as the passengers themselves. We want a rail sector that encourages innovation, encourages future development of people, process and technology to support an enriched economy in the UK and a better environment. So if you move on, thanks, Jacob. So here are some ways that in the world of track engineering, we're responding to some of these challenges. So starting at the top left, that nice shiny yellow train there is one of our dedicated trains that measure aspects of the infrastructure, from equipment mounted on the train, travelling in many cases at the line speed, so it doesn't interrupt the normal timetable. However, we need to do more measurement to allow us to learn more about how the railway is changing over time. So now we're looking at systems fitted to passenger vehicles. Unattended monitoring is the technical term. So we have systems already fitted to the IET, the Azumas, and the IETs running on the Great Western Main Line, which can measure track geometry from on board a passenger vehicle. And our challenge now is to integrate the data that those trains collect with our corporate systems that tell our frontline engineers how stable their track position is and whether they need to go and do some enhanced inspection or maintenance. And further across the top, there's more examples of how we're using technology like image analysis with cameras mounted on trains to pick up features. In this case, you can see a clamp attached to a rail to support a rail defect before we make a repair. So we can do things like check whether that clamp is properly fitted, and we have built algorithms to do that kind of thing automatically for us. So a glimpse really into the future of AI. And then towards the bottom, as well as train-borne systems, we have fixed monitoring. So we fit sensors to the track. Obviously they don't move, but they're there to detect changes in assets where we've got more concern, or we know there's more risk potentially with how that asset degrades. So again, it's about providing more data, converting that to real knowledge about the asset for our engineers, and giving them some early warnings of the need to go and conduct some maintenance. If we move on, thanks, Jacob. Some other developments. So across the top, you can see some more equipment fitted to our trains. This is designed to inspect the rail. So the kind of rail defects Brian was talking about earlier. We have sensors that run along the top of the rail at 35 miles an hour, inspecting the inside of the rail with ultrasound to look for small cracks. We also have laser mounted systems looking at the shape of the rail to look for wear. And then more into Richard's world, we have systems that look for the measure the forces on the pantograph and the overhead line equipment. And we're also looking at R&D into systems that can inspect the contact wire itself, looking for defects, a bit like the rail version, looking for cracks and things that might actually cause the contact wire to break. And across the bottom, this is really where we're getting into the world of robotics and automated inspection and maintenance. So we've got a small sort of tired vehicle they can see on the left-hand side, and we're developing welding systems and inspection systems we can fit to that. And the idea in the very long term is to have sort of autonomous drone technology that can get itself safely to and from a site where some maintenance is required, conduct the maintenance, record the output from that maintenance and leave the site, and really without really involving an operator. We're a long way off that at the moment, and the first stage is to automate more of the process with an operator to support that. But examples really of where we're introducing quite exciting new technology to enhance the way we maintain track and to reduce the cost and disruption that causes. Next slide, please. At the heart of this really is our management of data. We are collecting more and more data. We're now learning how to process that data so that we're generating some really valuable information from it. So we can look at not just the condition at any one point in time of a piece of our asset and piece of the infrastructure, but how that condition changes over time. And that gives us a better idea of risk really. And it's all about managing risk, as you've heard from earlier presenters. So by better integrating data, by providing information to frontline engineers and the maintenance and inspection teams, rather than just data, we can improve and enhance the way we look after our asset and provide a better service to our passengers and freight users. You can move on now, thanks Jacob. And really just give you an idea of, from a track technical strategy point of view, what are some of the key themes, so you can read them there. It's about optimizing simulation so that before we introduce new equipment, new technology to the railway, actually we've given it a really good testing, both in a kind of a simulation environment, but also in the lab-based testing, the kind of thing Rich has outlined there for the sort of overhead line and clearance development. We want to use new materials and advanced manufacturing to give ourselves better components that don't degrade as quickly, but also use less materials and perhaps use more recycled content feeding back into that decarbonisation piece from earlier. I've touched on automation already, but it's about, can we introduce 100% automated, non-intrusive monitoring and fault diagnosis? 100% might be a bit of a stretch, but we need to set ourselves some challenging targets, and it's about less disruptive access to the railway. And really, the key item, the bottom item is quite key as well. So there is lots of existing technology already available to us. How do we make ourselves more agile so we can introduce and implement some of this more quickly and more effectively? We can move on now, thanks Jacob. So I think this is my last slide, and really I've talked through a bit of technology there in the last few minutes, but the railway is all about its people. Everyone matters, really does matter. Without our passengers, we are nothing. It's about preventing it's about making sure that the picture in the middle top there, we prevent that happening. It's about working with all of our stakeholders and partners across the railway to come up with solutions that improve service, improve safety. I encourage you to really pick up from some of what Kamini said about going into your new careers with that spirit of thinking of ways to how we can improve what we do, the continuous improvement cycle. We have to sort of introduce new ideas. We have to listen to everyone's opinion, and we want a diverse range of thinking, diverse opinions, so that we can improve how we operate. So really, I really encourage you to always look for those opportunities to make improvements in your immediate role that you're going into, but also kind of more widely how your team operates and how that team operates within the wider part of the rail industry, whichever part you're operating it and working in. So people, you're so important. It's fantastic you're joining the rail industry. We need this kind of continuous input of new ideas, new thought, and please don't let anybody get in your way if you've got a great idea that you want to share and you want to try and get some sponsorship for. We really need people to challenge the way we do things currently. So that's it. Thanks, Jacob. I think the next slide's the end.
That's great. Thanks so much, Gareth. And I think, yeah, really important point you made at the end is about diversity of thought and how we need lots of different approaches in order to actually make the innovations that we need for the railway to work better in future. So very good, thank you. We've got just a few minutes left. Can I just ask all the speakers to come back on screen if possible? And we'll just wrap up. I think we've pretty much run out of time for Q&A. Though I could actually, I've got one quite good question actually, but I'll quickly ask, which should be quite a short answer hopefully. So it's from I think Tamaris Mapisa. He wants to say, can the surface of the rail become uneven due to cracking and peeling, and can it be resurfaced chemically, or do you have to resurface the entire rail? So Brian, that might be one for you.
Yeah, certainly. We are looking at techniques. One way, the crude way perhaps, is to machine off the surface damage layer. So we optimize or use grinding and milling on-track machines that actually remove a small amount or a large amount of material to remove that. We are looking at ways of perhaps resurfacing the rail, but it's quite a challenge to carry out welding on long lengths of track like that. But yes, it's something we're actively looking at, and certainly with some of the advanced material processing available, the potential of looking at cladding and coatings of either thin coatings or thick coatings to improve performance there. So yes, it's something we're actively looking at, but we do carry out a program of grinding regularly across the whole network, milling in certain locations to remove surface damage, but there is a limit how far we can go before the rail is effectively worn out. It's no longer a big enough section then. So, but yes, something we're actively looking at.
Sure, thanks. Cool. Right, I'm going to finish up there, I think. So thank you everyone for coming to speak to us. It's been really, really interesting. I think pretty much every presentation could have been an event on its own. So it was really great to have all these different subjects in the same event, and I hope that everyone online has found it really interesting as well. I'd just like to say thank you to Jacob Cooper from YRP, who's been in the background. We're weaseling around on the tech and answering all the questions that people have been asking. So thanks, Jacob. And also just urge everyone online, if you're new to the rail industry, if you're in the first 10 years, I would recommend that you check out YRP. We've got loads of different opportunities. No matter where you are in the UK, you can come to events, you can network. It's just a really great opportunity, and it's a really good way to kind of find your way within the industry. So yeah, again, thank you everyone. Thank you for Network Rail, and really great words and really interesting presentations today. So I'll let everyone go and have a really good evening, and we'll see you next week for our next session. So, thanks very much.
Thank you for everyone attending.
Thank you, Isabel. Thank you everyone for presenting and for attending. Cheers.
Thanks all. Bye.